On January 20th, 1974, the F-16 was not supposed to fly. It was supposed to race down a runway and stop. Then a small control input became a violent roll oscillation. The right horizontal stabilizer and a wingtip scraped the runway. Test pilot Phil Oostracher had seconds to choose: abort and risk losing the prototype, or take it into the air. He chose the sky. 6 minutes later, the aircraft was back on the ground. Its official first flight was still almost 2 weeks away, but the fighter had already revealed the tension that would define it: a lightweight airframe, deliberately responsive handling, and a computer-mediated control system built to turn instability at the edge into precision in the pilot's hand. More than 50 years later, the silhouette is still familiar. The F-16 inside it is not. So why is an aircraft born in 1974 still being rebuilt for tomorrow? This is the F-16 Fighting Falcon, known almost everywhere it flies as the Viper. Its longevity is not the story of an airplane that refused to change. It is the story of an architecture that kept absorbing change: new missions, new weapons, new sensors, new software, and new safety systems, all inside one of the most recognizable fighter shapes ever built. To understand why it lasted, we have to begin before it had a name. When the United States Air Force asked whether a smaller, lighter fighter could produce extraordinary performance without the size and complexity of the aircraft around it. The F-16 emerged from the Air Force's lightweight fighter prototype program. The wager was not that a small aircraft would automatically be better. The wager was that carefully controlled weight, high thrust-to-weight performance, strong energy maneuverability, and simpler support demands could create a remarkably effective fighter. That meant treating weight as a design discipline, not simply a number on a specification sheet. Every extra system competed with fuel, acceleration, turning performance, maintenance access, and cost. The prototype had to demonstrate that the balance could work in the air, not merely on paper. The F-16 and Northrop F-17 became the program's two prototype competitors. In January 1975, the Air Force selected the F-16. What began as a lightweight experiment would become something much larger because the final aircraft did not preserve the prototype as a museum piece. It created room for an operational system to grow. That outcome can make the original argument look obvious in hindsight. It was not. A light prototype still had to become an aircraft that could be produced, supported, armed, trained on, and operated in real units. Range, radar, weather capability, safety, reliability, and mission flexibility all pulled against the discipline that had made the prototype exceptional. The enduring achievement was not simply keeping the aircraft light, it was carrying the logic of the prototype into an operational fighter without losing the qualities that made it worth selecting. That tension never disappeared. Every later edition still had to earn its place against weight, electrical demand, cooling, maintenance burden, and cost. The F-16's evolution is therefore not a story of unlimited growth. It is a long negotiation between new capability and the physical limits of the airplane carrying it. The central design choice was not a single engine, a blended wing-body shape, or even the bubble canopy. It was the relationship between the aircraft and its flight control system. The F-16 uses fly-by-wire control. The pilot's commands are converted into electrical signals. Flight control computers interpret those inputs, then command actuators that move the aircraft's control surfaces. That description can sound as though wires merely replaced cables. But the deeper change was behavioral. The control system could continuously shape how the aircraft responded. It could help make a deliberately responsive airframe feel predictable and precise to the pilot. The correct term is relaxed static stability. It does not mean the F-16 is simply an uncontrollable aircraft held together by software. It means the design reduced the natural tendency to return toward its previous attitude, trading passive stability for faster response and then using the flight control system to manage that response. The pilot still decides what the aircraft should do. The computer translates that intent into thousands of small corrections the pilot does not have to command individually. Pilot, computer, control surface, aircraft response. Then the loop begins again. The flight control philosophy was matched by a cockpit built around visibility and workload. The bubble canopy gives the pilot a wide field of view forward, above, and to the sides. The seat is reclined about 30 degrees. The control stick is mounted to the pilot's right rather than between the knees, and it senses hand pressure to send commands into the flight control system. None of those features is a party trick. Together, they create a cockpit philosophy. The pilot is positioned to see, decide, and command, while the aircraft handles the translation between intent and motion. The side stick also changes the physical relationship between pilot and airplane. There is no long center stick sweeping through the cockpit. A relatively small hand movement, or more precisely pressure, becomes a full aircraft response through the control system. The result is not that the pilot matters less. It is that the aircraft is designed to preserve the pilot's attention for the tactical problem rather than the mechanics of moving control surfaces. The original lightweight fighter debate often gets compressed into a simple phrase: small day fighter. The operational F-16 did not remain there. As the aircraft entered service, the mission system expanded. Navigation and attack capabilities grew. Precision weapons, beyond visual range missiles, targeting pods, night operations, suppression of enemy air defenses, reconnaissance, and other missions were integrated across different blocks and operators. This evolution matters because it explains the difference between an aerodynamic design and a military platform. The aerodynamic shape can remain recognizable, while the sensors, software, displays, weapons, and mission data inside it change repeatedly. Not every F-16 has the same equipment. Not every operator follows the same upgrade path. Block numbers, national configurations, and mission requirements matter. But the larger pattern is clear. The platform expanded by adding capability in layers rather than by pretending every aircraft was identical. The silhouette became a container for different operational systems. Long life is often explained with a list. There are many F-16s, many pilots, many maintainers, and many countries that operate them. All of that matters, but installed fleets do not remain useful automatically. They remain useful when the aircraft, support system, and upgrade path can keep meeting real missions at an acceptable cost. The Air Force's fact sheet notes that built-in provisions added to the structure and systems beginning in the early 1980s enabled later flexibility for precision strike, night attack, and beyond visual range interception. That is the hidden engineering story. Growth is easier when power, cooling, space, interfaces, software, and structural provisions exist, or can be added without rebuilding the entire aircraft from the ground up. The F-16 was not designed in 1974 with every future sensor already imagined. It survived because its architecture could accept systems that did not yet exist. That acceptance is rarely as simple as removing one box and installing another. A more capable sensor can require more electrical power, additional cooling, different cockpit displays, new software, revised mission data, new maintenance procedures, and testing across the rest of the aircraft. A weapon is not truly integrated because it can be attached to a pylon. The aircraft must recognize it, communicate with it, present usable information to the pilot, release it safely, and support it throughout the mission. This is why interfaces matter. The visible upgrade may be a radar, display, pod, or missile. The deeper upgrade is the chain of connections that lets the new system become part of the aircraft rather than cargo hanging from it. Modernization is easiest to see in the nose. Some Air Force F-16 units have received active electronically scanned array radar upgrades. AESA technology can steer radar energy electronically rather than relying only on a mechanically moved antenna. The exact capability depends on the radar, aircraft configuration, software, and mission. The important point is not that every F-16 suddenly became the same. It is that a decades-old airframe could accept a substantially different sensor architecture. Behind the radar are processors, displays, software, electronic warfare systems, communications, and weapons interfaces. Modern Block 70 and 72 aircraft are manufacturer-described with new avionics, AESA radar, an upgraded cockpit display, and automatic ground collision avoidance system. Those product claims belong to the manufacturer and must be understood in the context of the exact customer configuration, but they demonstrate the larger principle. Today's production F-16 may look familiar from a distance while sharing remarkably little mission system experience with the earliest operational aircraft. One of the most important additions is not a weapon. Automatic Ground Collision Avoidance System, GCAS, was developed and tested through Joint Air Force and NASA work for the F-16. The system monitors the aircraft's state and terrain relationship. If it determines that ground impact is imminent and the pilot has not responded, it can command a recovery maneuver. That sequence matters. Detect, warn, decide, recover. GCAS is not an autopilot that replaces judgment throughout the mission. It is a narrowly focused safety system designed to intervene in a final window when the aircraft is on a collision path with terrain. It also shows how the meaning of performance changes over time. A modern combat aircraft is not judged only by speed, turn rate, or weapons. Software can create safety performance that the original airframe never possessed. Software can be replaced quickly. Airframe fatigue cannot. Every flight loads the structure. High-G maneuvering, landings, vibration, and time accumulate in metal and joints. Eventually, a fighter's remaining life becomes a physical engineering question. The Air Force's Service Life Extension Program was designed to extend selected F-16C and F-16D aircraft from 8,000 flight hours to as many as 12,000. That statement applies to selected aircraft and a specific program. It is not a universal promise for every F-16 ever built. The work involves inspection, analysis, and structural modification. It is less visible than a new radar, but just as decisive. An aircraft cannot carry modern avionics if the structure beneath them cannot safely continue flying. This is what longevity looks like up close. Not one airplane flying unchanged for half a century, but a sequence of repairs, replacements, upgrades, and engineering decisions that renew different parts of the system at different times. The F-16 persists because several advantages reinforce one another. There is a large operating community. There are trained pilots and maintainers. There is a mature logistics network. There are established training systems, weapons integrations, infrastructure, suppliers, and partner relationships. There is also a design that can still receive meaningful upgrades. None of those reasons works alone. A large fleet without modernization becomes obsolete. An upgradable aircraft without a support network becomes difficult to sustain. A capable fighter without trained people and available parts becomes a hangar asset. Together, those elements form an ecosystem. That ecosystem lowers the friction of keeping the aircraft useful and creates a market for new production and continued upgrades. It also creates feedback. Operators generate experience. Maintainers identify recurring problems. Test units evaluate changes. Suppliers build replacement parts and new systems. Training organizations turn those changes into procedures. A modification that proves valuable in one part of the fleet can inform work elsewhere, even when individual national configurations remain different. Scale does not make every decision efficient, and it does not erase the cost of aging equipment. It does, however, give the platform something a rare aircraft can struggle to maintain: enough people, infrastructure, and demand to justify continued engineering. The F-16's installed base is not merely a count of airframes. It is a network that keeps producing reasons and mechanisms for the aircraft to evolve. The most durable military platforms are often not the ones that remain frozen. They are the ones surrounded by enough engineering, industrial, training, and operational capacity to keep changing. Longevity is not invulnerability. The F-16 comes from a design era before low observable shaping, deeply fused sensor architectures, and the survivability requirements associated with the most contested modern airspace. New sensors and weapons can improve what the aircraft sees and does. They cannot transform the underlying airframe into an entirely different design. That does not make the aircraft irrelevant. It defines its boundaries. Different missions place different values on cost, readiness, payload, range, support, interoperability, survivability, and sensor integration. The useful question is not whether the F-16 defeats a newer aircraft in an imaginary ranking. It is whether a specific F-16 configuration can perform a specific mission inside a specific threat environment. The answer can be yes without pretending the limitations disappeared. The F-16's first flight became memorable because it happened before it was planned. Its survival is almost the opposite story. For more than 50 years, people have planned, tested, repaired, upgraded, and rebuilt the system around that original airframe. The flight controls made a deliberately responsive design practical. The cockpit centered the pilot's view and intent. The mission architecture accepted new layers. The support network turned upgrades into an ecosystem. And structural work kept selected aircraft flying long enough to receive them. The F-16 did not remain relevant by staying the same. The silhouette is familiar. The system inside it is not. That is why the F-16 is still here.